Yeah, I'm James Forshaw. I'm here to talk about abusing symbolic links on the Windows platform. I've got a the obligatory background, so I'm currently a researcher for Google's Project Zero team, and I tend to specialize in Windows, but I will look at other operating systems, but Windows is my main thing. And I like logical vulnerabilities. I like finding sort of things like privilege escalations, because you can find some interesting fun bugs which are slightly more interesting than your typical memory corruptions. So what specifically am I actually going to be talking about? So I'm going to be talking about the different implementations of symbolic links on Windows, and from that, what sort of exploitable bug classes you can find, which symbolic links are a useful tool to actually perform the exploit in. Now, I've got a few example vulnerabilities which are all fixed, obviously, but they're all sort of examples of fairly simple vulnerabilities which wouldn't be exploitable probably without symbolic link support in the operating system. And there's also a few offensive exploitation tricks. So obviously, if you find a bug which can be exploited in this fashion, I've got a few tricks in here which you can then abuse to actually do the exploitation itself. Now, is anyone actually willing to admit that they do not know what a symbolic link is? Okay, that's pretty good. How many people are actually telling the truth? I don't know. But symbolic links are something which has traditionally been is more thought about on sort of Unix platforms. So a symbolic link is basically a way of linking two files to each other, and instead of actually doing like a physical link between the files, say writing a sort of a directory entry which references the original file, which would be usually a hard link, a symbolic link instead, they write a string which represents the path to the other file into the file system, and then when the kernel tries to open that file, it will read out that string and follow the path which was in there. So this has numerous advantages. For example, you can span between different file systems, so a sort of physical link wouldn't be able to do that. And it basically is a very simple thing to do, and you can do this on a Unix system without any privileges required. But of course, with any sort of useful feature, there's always some way you can use that to attack the system. And it's pretty well known that symbolic links on Unix systems can be quite dangerous at times, because it allows you to do fun tricks and actually exploit vulnerabilities in generally privileged services. And this is usually used to gain additional privileges so that you can elevate to root, for example. So there's I identified sort of three main vulnerabilities you can exploit using symbolic links. The first one is sort of arbitrary resource creation or overwrite. So this is where you have a privileged service, a privileged application, which is writing to a known location on the file system. Say it's writing to the temp folder, and it's writing a particular file name. Now that, in and of itself, is not necessarily dangerous. But what you can do as an attacker is if you can drop a symbolic link into that location, you can instead redirect that resource creation or that resource overwrite to an arbitrary location. And potentially that can be used like to set up a cron job or other similar techniques and actually gain privileges. Now sort of the inverse of that vulnerability is information disclosure. So again, you've got a privileged service, but this time it's reading some sort of file contents. It's reading a known file out of the temp folder, for example. Now in this case, again, we can drop a symbolic link, but we instead point it to something we want to read, which we would not normally have permissions to do. For example, the shadow file on a Unix system. We obviously still need some way of getting that privileged application to disclose that read information, but that's just a byproduct of the vulnerability. You've got to actually find a way of exploiting it that way. Now the final sort of class of bug I really identified is time of check and time of use attacks. This is where you have a privileged service that tries to open a particular file and does some sort of checking on it. So it checks, such as like signing, for example. So it checks that executable is signed or a package is signed, and then will do something with the result. But because symbolic links are really lightweight, and there's nothing like locking which will get involved, you can easily use this to switch out the location of the file and exploit these time of use attacks. And we'll see a few examples of these on the Windows platform as we go along. Now, symbolic links are only something which actually really affect the NT line of Windows, but then again, basically, there is no other version of Windows really available anymore. But it's been there since day one. So in NT 3.1, two types of symbolic links were created. The first one, object manager symbolic links, and then registry key symbolic links. But these were not file level APIs. So this is not sort of symbolic links in the traditional Unix sense, where you put a file and that's a symbolic link. These were instead very specialized types of symbolic links for specific purposes. It wasn't until Windows 2000 came along where the first file system level symbolic link was actually introduced. This is the mount points or the directory junction support. And this allows you to link directories to other directories or other devices and other drives. So it wasn't file level, but it was directory level. So you couldn't drop a file in temp, but you could drop a directory in temp which would redirect somewhere else. We had to wait until Windows Vista came along in 2006 before we actually got file level symbolic links. And actually it turns out they're not as useful as it seems, as we'll see later on, but this was the first time where we actually had something comparable to sort of the Unix style symbolic links. So this part of the presentation, I'm going to go through the different types of symbolic links and sort of generally give sort of example vulnerabilities of how they could be abused and what sort of features you can use in them to actually do some fun stuff. So we'll start with sort of probably the most important symbolic link on the Windows NT operating system. This is object manager symbolic links. And if you use Windows at all, have ever used Windows, you've probably used object manager symbolic links without ever necessarily realizing you're doing so. Because the drive letters are sort of simulated artifacts of the operating system. So when you go to the C colon drive, you're actually following an object manager symbolic link to the real device, the real file system. And you can see it here in the little screenshot that we've got C colon going off to some arbitrary location. Now the object manager is responsible sort of like for the deep level parts of the NT operating system. It's usually fairly hidden from your usual programming environment. It only sort of appears once you sort of dig into the native API layers. But it's used for pretty much everything. So any object which can be named on the operating system can be put into this sort of object manager namespace, which is sort of a secondary file system on the operating system. So we've got files. So we've got opening C drive or opening name pipes, for example. The registries hands off this object manager namespace, and even things like semaphores. So synchronization primitives can be named and can end up in the object manager namespace as named objects. So it's really easy to create object manager symbolic links. It's not strictly documented to do so, but the actual parameters you pass to this NT create symbolic link object system call are pretty easy to work out. And using this piece of code, you can create an arbitrary object manager symbolic link as long as you have access to the directory in the object manager namespace. Now, the important thing about how sort of these object manager symbolic links work is kind of actually how they're implemented under the hood in the kernel itself, because this leads to some interesting properties later on as I go into more depth of things like file level symbolic links. So say I'm trying to open a named semaphore. So there's a system call NT open semaphore, and you pass it a string which represents the name of the semaphore object you want to open. That effectively just passes off to an internal function, part of the object manager, which is open object by name, which then calls into an internal function lookup object name. And this is where the actual sort of magic happens of parsing that name out and actually working out what the destination object actually is. So in this case, it separates everything using backslashes. So all the paths use backslashes as the path separator. And first we look at the first path component. In this case, my objects is a directory, an object directory, which is actually distinct from file directories. It actually has its own system calls you need to use to create and query them, but effectively they're roughly equivalent to file directories. So it looks through that and tries to find the next path component, which in this case is global. So it finds global, and it reads its type, and it realizes it's a symbolic link. So it goes, okay, I now need to handle this in a particular way. So what it does is it calls an internal function again, parse symbolic link, which then reads out the string, which is contained in this object, and actually does the translation of the path. So in this case, global actually remaps to this base named objects directory, and so the function actually rewrites the current path for you. But now we've got a problem. We're kind of deep into the lookup process. We're currently parsing this symbolic link. So how can parse symbolic link actually tell the object manager, hey, you kind of need to reparse this path because everything's changed. So you need to restart the whole operation again. Now, obviously, you could just recall lookup object name, but then doing recursion in the kernel is probably a bad idea. So what it does instead is it returns a special status code. In this case, status reparse. And this tells the object manager, hey, you may want to go back and reprocess that path, and it can keep doing this up until the point where it hits like a fixed limit of reparse operations. Because obviously you don't want to spin forever trying to open a symbolic link. Eventually, either it runs out of symbolic links to follow, and it finds nothing, and so it can't open that semaphore, or it actually finds a named object, it opens it, and actually returns it back to you. So there's a few things we can do with this as an attacker. The types of bugs we can actually exploit are, the most obvious one is object squatting. This object manager namespace is used to represent the named objects in the system. But in fact, file symbolic links are more likely to be exploitable because it's just a case of, it's easier to find these sort of vulnerabilities. You can just stick them in process monitor, look for errant accesses to files, and potentially attack it that way. So this is an example of vulnerability I found in the enhanced protector mode broker for IE11. And it was in a function, motw create file, and allowed you to open any file as a normal user. Now that doesn't sound like a particularly useful vulnerability, but when you're in enhanced protector mode, because of the way the security works, pretty much all the files for the user, so system files you can open, but the user's files themselves, generally you cannot actually open. So this was an information disclosure. It would allow you to open arbitrary user files and say read their credit card details or something like that. So the function was pretty simple. It had a couple of checks. The first one, it said, does it have marketer web? And marketer web is a way of marking a file as coming from the internet. So it could be, for example, you have the zone identifier stream, which has a particular zone, or it's set as a low integrity label. But then there was a second check, is URL file. And all this did was it said, if our file name ends with .url, then it's clearly from the internet or is some useful internet property, and so just pass it to create file and let them open it. Now, if you've got file level symbolic links, that's something you can obviously directly exploit. You can create a symbolic link with a .url extension, and you can then open arbitrary files. But then the question becomes, how can you actually exploit this using object manager symbolic links? And this is where you have to sort of understand the fun of the Win32 path support. So you've got a couple of standard path types. So you've got relative paths, or you've got absolute paths relative to a derived letter. And they're not that interesting for our purposes. But what we do have is these two ones at the bottom. These are the device paths. And there's a bit of difference between the dot version and the question mark version, but effectively, they do basically the same thing. And that is, it allows you to get into the object manager namespace via the Win32 create file call. So say we've got this particular path, so //./ c:, blah. It calls an internal function in create file to translate that into a native NT path. And all effectively it does is it replaces that leading //dot with /?, which is referred to as the DOS device prefix. And I've already pointed out that C: is a symbolic link. So effectively what happens, it rewrites that path. It ends up calling the actual opening an arbitrary file for us. So one way of attacking this would be if we could write to that DOS device location, just add a brand new drive letter. But we can't. We don't have permissions to do so from EPM, so we're kind of stuck. But if you look at the DOS device list, there's a very interesting symbolic link there. This is called global root. In global root, if you look at it in, say, the WinObj tool, you'll notice it has an empty symlink path. So what does this actually do? Well, if you put global root there, instead of putting, say, C:, the first translation is the same. It puts the DOS device prefix in the front. But after the lookup, the symbolic link has replaced that entire sort of front-end part. And all of a sudden, we've now ended up in some arbitrary location in the Object Manager namespace. So all we now need is one location which we can write to in the Object Manager namespace as EPM, because to create Object Manager symbolic links, you require no specific privileges other than being able to write to an Object Manager directory. So there's one for EPM, which is created for sort of app container stuff, which you can create arbitrary symbolic links in. So actually exploiting this is really simple. You created some arbitrary symbolic link somewhere with a .url extension, pointed at any file you like, and just call this create file call. It would pass the URL check, but would open whatever file you specify for read access. So pretty simple attack, and a fairly good demonstration of just something which you can just abuse from these sort of calls. Now, I'm not going to go too much into registry key symbolic links. If you want to see more about them, like my IE presentation last year at Infiltrate contained an attack which you could escape from enhanced protected mode using registry key symbolic links. But the thing which is just interesting to point out here is how the kernel opens registry key symbolic links. So we call NT open key, which is equivalent to, say, NT open semaphore. That then calls open object by name, which then calls lookup object name. And hopefully you can probably see where this is going. So instead of parse symbolic link, you now have parse key, which is part of the configuration manager. And this sees that it's a symbolic link key and reads out the symbolic link, and obviously rewrites the registry path, returning status-free parse to force the object manager to relook up the path. Exactly the same, just with a slightly different technology. But unfortunately, registry key symbolic links are not actually that useful. So Windows 7 fixed a number of issues. They blocked, for example, symbolic links between untrusted user hives and trusted, say, local machine hives. And it also turns out the symbolic link has to be a valid registry path. So you can't just return any arbitrary path into the object manager. It has to match some sort of existing registry key. But you can still use it to exploit some vulnerabilities. So EPM, especially, you can use it in there because usually there's places you can write to in EPM mode. And again, you require no special privileges to do this. And then all you need is a higher privileged service to write into a registry key to do something useful. And the interesting thing is the mitigation for this using the Win32 APIs is not actually documented. If you look at the documentation for it, that function, it recommends you can pass only 0 to a specific flag, and in fact there is actually a secret hidden flag you can send, which will actually make sure that you don't accidentally open symbolic links. So the third technology I'm going to talk about is mount points, or directory junctions. And the naming convention is dependent on how you're using it, but actually it's the same technology under the hood. So mount points are usually considered when you point a directory to another drive, and directory junctions are where you just point it to another directory on the same drive. But they are effectively the same thing. And latest versions of Windows, the command prompt actually has a mklink command which you can use to create these directory junctions for you. And surprise, surprise, they look remarkably similar again under the hood. So in this case, instead of calling parse symbolic link or parse key, we now call parse device. And parse device goes into the NTFS driver and tries to open a particular file, which obviously is our mount point, which we've set. This is held, for NTFS, held in the $reparse point stream in the NTFS directory, and that just contains the substitute name to reload. And once again, once it's rewritten the path, it forces back status reparse, and the object manager then proceeds to relook up the object path. So what does it actually look like from a programming perspective? Well, that reparse point data has some sort of structure in it which defines the entity name, defines other sort of properties of that reparse point. And this is what it sort of looks like. So you've got a reparse tag. This indicates the type of reparse point, and as we'll see, it's used for different things later on. We've got the data length, and then we've actually got the reparse data itself. And this contains pointers to the substitute NT name, and pointers to a print name offset, and then the actual data itself. So it's all in one contiguous structure. And creating it is just as simple. There's a file system control code. You pass that reparse point buffer and the handle to a directory, and as long as you've got write access, it should write that reparse point. And again, no privileges are required to do this whatsoever. As long as you can write to that directory, then you can do it. But it turns out there is actually a few limitations to this. So unlike, say, a standard file level symbolic link, one big problem is that directory must be empty. So this precludes you from doing fun attacks like changing the temp directory to a junction point. Because there's a good chance there's going to be files in that temp directory which are not owned by you as a low privilege user, which you can't get rid of, you can't delete. The actual target device, so once the reparse process occurs, when it goes back into the I/O manager again, it limits you to very specific sets of device types. So it allows you to do disks, CD-ROMs, tape drives, because obviously you need to have a mount point to a tape drive. But this means you can't point it at, say, remote UNC shares or SMB shares. So let's go through another vulnerability I found in the task scheduler service. And the thing about this is obviously it uses mount points, but that in itself isn't that interesting. But I'll show you an interesting technique to actually win timer check, timer use races when encountering symbolic links, which makes the reliability of exploiting these vulnerabilities much, much higher, as long as you can meet the conditions. So the bug was this. When you go to run a scheduled task, there's a task file on disk under the System32 tasks folder, which contains the contents of that task. Now, the first thing it does when you go to run it is it reads in the file and it hashes it. Now, originally there was a bug, which I believe Stuxnet exploited, where they used CRC32 for the checksum, which wasn't exactly resistant to collisions. And now modern versions of Task Scheduler use like SHA-256. So you can't really exploit this from a sort of collision perspective. But one thing you can do is you can obviously corrupt that file. And at that point, the SHA-256 hash will no longer match the other hash. Now normally all this is done as under impersonation. So it's done as the normal user who is calling that task to run it. But I found one edge case where the scheduler service forgot to impersonate it during a file write. And this is when the file hash didn't match the original hash. It would rewrite that task file back to the original location, but it forgot to impersonate. So it would run as a local system. So obviously we can drop a mount point here because it turns out you can just write to this tasks folder as a normal user. You didn't need to actually go via the service, which in many respects I think is a bit of a mistake. But unfortunately, it's probably cast in there now and you can't get rid of it. So we can just drop a mount point there. So obviously we've got some sort of hash process. We've then got some sort of nebulous timing condition, which we can hopefully exploit before the task file gets rewritten, and we can hopefully get a file written outside of the task folder at local system privileges, which means we can write to anywhere we like. So how can we actually exploit this? Well, there's two events going on. There's two file opens. The first file open, it opens it for read access to do the hashing of it. And the second file operation is where it reopens the file for write access and writes to it. And that's that timing window. So if there's a way we can trigger if there's a way we can catch the process trying to open that file for read, we can potentially switch the symbolic link underneath it and do it sort of 100% guaranteed arbitrary override. And I realized that there's a feature which was introduced in Vista and has been improved as time has gone on, called opportunistic locks. And this has a very interesting property in that it allows you to set a lock on a file, but set then a event callback which will get signaled when someone tries to open that file and wants to release the lock. The point of this, sort of from an operating system perspective, is for things like search indexes. When you're indexing someone's content, say their Word documents, it can open this and put an opportunistic lock on that file. Now, if you then want to open your document, you'd be kind of annoyed if it just gives you the traditional sort of, sorry, this file has been locked and you can't open it. It would kind of annoy you. So this allows the search indexer to get signaled when someone's trying to open that file and just close the file and get out of the way. And yes, okay, its indexing will have to be redone at some later time, but it at least means that the user doesn't see arbitrary files getting locked accidentally. But we can abuse it for our own purposes, because this signal is a perfect flag for when we need to actually change the symbolic link. So it works something like this. We go and set up a junction to an arbitrary location beforehand, and then write our task file to that location. We then can modify that task file so it's now corrupt, or at least doesn't match the SHA-256 hash, and place our op lock on that file. So this op lock will trigger when anyone tries to open it. So the task scheduler service tries to open the file, and we immediately get called back. We get an event set which says, hey, someone's trying to open this file. Maybe you want to let them do so. But crucially, it's stalled in the I/O manager. So this pending request is sitting there in the kernel going, yeah, I'm waiting for you to release the file, come on. And obviously, we're in no rush to do that. So we just changed the mount point now at this point. But because the I/O manager already knows the exact file it's trying to open, this is past all the points where the mount point is being handled, the repass point data is being processed. So it's definitely opening that my task file, but it's obviously not, it doesn't care about the mount point anymore. So we can quite happily change that mount point to point to Windows instead. We can then release the op lock, which will restart the scheduler service. The scheduler service can now process the hashing of that file, finds it's incorrupt, and goes, right, okay, I now need to write back to that task file, which obviously is now a symbolic link somewhere else, and we now write my task to Windows. And we could choose whatever file name we liked, and potentially then, from that, gain privilege escalation from that. So nothing's ever perfect. So there are some limitations to your use of opportunistic locks for doing these time check, time use attacks. One of them is you can't block on access to attribute reads. So if someone just tries to read an attribute of that file, tries to read the access control list, we cannot actually lock on those types of operations. And it's also one shot. So once it's been fired, you kind of have to close the file handle and release the op lock. And there's not an easy way of re-establishing it, but there's various tricks like chaining directories up to get to different locations to do this. And you can also, at least on Windows 8.1, you can put op locks on directories. And so when an operation such as parse display name tries to process a directory path, you can actually get signal back in that operation. So just to demonstrate the point that it actually does do what I say in the tin. So I've got a set of tools I wrote for doing symbolic link testing, symbolic link attack testing, basically. Obviously, it won't find you vulnerabilities, but if you find a vulnerability, you can potentially use it to test whether you can actually exploit it in real terms. So in this case, I've got just a file.txt with some content, and I've got my symbolic link tool, which called set op lock, and we can just put op lock and file.txt. Okay. So we get no output back from that. But if we now go and try and open that file, so we can just open it in, say, Notepad. We see Notepad now stalls. Notepad is completely unresponsive. But we've been told our opblock is fired. So if we now hit Enter on there, we should now find Notepad springs back into life, and we can actually now do that. And so, obviously, in the task scheduler's case, that was obviously doing it all automatically, but it just demonstrates that it can be done. So the final type of symbolic link I'm going to talk about is NTFS symbolic links. And as I said in the sort of preamble, this was the first time where you had full-on file-level symbolic links on Windows. And you can use the make link tool to do that arbitrary linking for you. And the structure of a symbolic link on the NTFS file system is basically pretty much exactly the same as a mount point. In this case, the only difference is the reparse tag is different, and there's an additional flags value, which is because you can have either absolute or relative symbolic impacts. But you use the same operation to create the symbolic links as you do on mount points. Unfortunately, there's a problem with actually using this as a normal user for privilege escalation. And that is because, probably more for compatibility than security, the original designers added a new token privilege which was required to actually create these symbolic links. And unfortunately, by default, normal users do not have this symbolic link creation privilege. And so normal users, by default, cannot create these symbolic links, which is a bit of a shame. But that intrigued me enough to sort of go, okay, I wonder how it validates that. How does it actually determine whether I have the privilege to create a symbolic link? And if you actually look at the code, this is in ntfs.sys, if you've done any sort of kernel security work, you would expect to see something like a single privilege check for the particular privilege. But that's not what you find. Instead, you find that it's just checking this flag. So there's some sort of creation context, NTFS context, and it just checks a specific flag has been set. So where is this flag set? This flag set is done here. So if you've got restore privilege, it automatically grants you this flag. Or if you're in kernel mode, or if you obviously have this privilege. But this function is called during the file creation routine. So it's not called individually per call into device IO control. It is called explicitly when you do the creation. So let's think of a sort of hypothetical scenario where you might actually be able to exploit this. Say you have a kernel driver, probably not greatly written kernel driver, but one nonetheless, which opens some sort of log file for the user. But it uses it using the ZW create file call, which means that it will open that file with kernel privileges. Now we can't influence the destination of this log file at all. So for the most part, it's pretty secure to actually hand that handle back to the normal user. But in this case, just by doing that single action, you gain the privilege to write a symbolic link to that file, even though you do not actually personally have that privilege yourself. Now, I'm not saying such a driver exists, but it wouldn't surprise me if such a driver does exist. Okay, so that was slightly annoying that you couldn't use them, because that would be a really useful feature and kind of negated or anything else I had to worry about. So I thought, what else has symbolic support? And if you sort of read between the lines, SMBV2, which is the server message block version 2, introduced in Vista, also introduced symbolic links. That's interesting. And if you look at the specification, you can just download the specification from the Microsoft website, you'll see that the data structure it returns during this operation looks remarkably similar to a on-file symbolic link reparse buffer. But again, there's a problem. So probably again for security, because these are resolved on the client, not on the server, you could get a remote server to link from you to a local file or another remote file. And that probably has security impacts, you would assume. So actually, by default, even though SMBv2 supports symbolic links, every default client install and probably server install will not actually follow them. So it's kind of a completely useless piece of technology, because unless the admin explicitly requires these to be operational, they won't enable the support. So again, we're kind of stuck. We're kind of going, oh, well, we can't even use them on SMBv2 shells. Well, probably. So the question then arises, how is that enforced? Is it the SMBv2 driver which is doing it? Well, it turns out it's actually the I/O manager. So this is basically the same bit of code I showed before for mount points, which is checking the target device type. But instead, when you encounter a symbolic link type, it processes it there. And it basically checks, is the source target type and the destination target type, did they match our list of allowed operations? So if you go from remote to local, to network to local, is that actually allowed by policy? If not, return invalid data. So this is why you get the failure. You try this, and it's the I/O manager itself which represents whether you're allowed to follow that link or not. So that got me thinking. The standard specifically states that that reparse tag must be set to the symbolic link reparse tag type. But we've seen that effectively this reparse buffer is just bubbling back up through the I/O manager and is then getting processed as if it was coming from some arbitrary location. But of course, the SMBv2 driver is bound to be enforcing this constraint, you would hope. Unfortunately, it doesn't. The SMBv2 driver only calls a function which just says, is this buffer some sort of valid reparse point buffer? Doesn't matter what type of reparse point buffer it is, it just has to be one valid one. So, we can obviously exploit this condition. Because if we write our own custom SMBv2 server, modify Samba, for example, we can get it to return an arbitrary reparse buffer. So what happens if we pass back, instead of a symbolic link reparse buffer, we send back a mount point one? It turns out the I/O manager doesn't care, and because mount points do not check the source type, as long as you're pointing your remote SMBv2 symlink to a local file, that check will pass, and you can open any local file from someone trying to open an SMBv2 file. So obviously it goes back into the NTFS driver, and you can open the local file. So I'm going to go a quick demo of this. Hopefully I've got everything running. Okay. So I have a custom version of Samba running on just a little Linux VM. And I've modified it so that it returns these mount point buffers back to the caller. So it's controlled using just a little control file. In this case, I'm redirecting example.txt to this secret file on my hard drive. And I've got a HTML file. And what this HTML file does is it just uses XML HTTP request to load example.txt. And this only obviously works if we're running that HTML file from the Samba shell. So in this case, you would have to get someone to load this HTML file in IE from your malicious server. But that might be possible. Okay, so obviously we've got our secret file, so we want to obviously prove that it's working. So hello, Infiltrate. I don't think it really matters about capitalization. So if I now run this in IE, we get pop-up just saying to read the file, and then we'll read that content back out and redirect it to a HTTP server, so it just proves that you can egress it out into the internet. And we get, obviously our file has been pulled off remotely, but pulling the local file. Now it's worth pointing out that this bug isn't actually fixed, so if you can find a more useful use for it, then by all means. But yeah, it wasn't actually. Microsoft decided not to fix it for reasons I'm not quite sure on. But okay. So all this talk about file level symbolic links, it would be really awesome to have them, and we don't have privileges, because if you have privileges to create symbolic links, well, you can do whatever you want anyway, you're an admin. So I wanted to try and find some way of abusing this. Now, one interesting property of that SMBv2 bug is it demonstrates that even though mount points are supposed to be for directories, it doesn't actually matter from an object manager and IO manager perspective. You can actually redirect it to a file, and it would work as long as all things are equal. So that got me thinking, what if I just set a mount point pointing at a file? Would that work? Now, the first try of it, this is just using a quite useful tool to do file testing. The first result seems to be no. You get access denied returned. It says, I'm not going to open that file. Sorry, mate, it's not happening. But if you change the parameters of that create file call, specifically if you add the file flag backup semantics flag, it does allow us to open that file. And I'm not saying it opens the directory, it actually opens the target file of that symbolic link. So kind of we've got file level symbolic links. If we actually go a bit deeper and look at the native layer, we get what I refer to as the NT create file paradox, or refer to the file flags. When you open a file using native APIs, there's two flags you can set. One says, I want to open this, and it's supposed to be a directory. And if you try that on this symbolic link, you get back a status code which indicates it's not a directory you're opening. Okay? If instead you pass the non-directory file, which is one of the bizarrest sort of naming conventions, like you're opening files, yet you're giving priority to directories over files, but anyway, you get back, file is a directory. That's not very helpful. Turns out if you specify neither, so if you find a call, say, in the kernel, which specifies neither of these flags, then it will actually still open that file as if it was a symbolic link to a file, even though it's actually a directory. And you can do other fun stuff. Does anyone know the $index allocation trick? No? Okay. Basically, what it allows you to do, if you put a suffix on the end of your file name, $index allocation, which is a NTFS string type, it will actually open it as if it's a directory. And it turns out, if you try and open this link with this $index allocation at the end, it will still open the symbolic link. It will basically bypass that initial directory check and then open the target symbolic link. So there's a few tricks there which you can actually, in certain circumstances, exploit to get file level symbolic links. But we want something a bit more, I suppose, reliable, something which doesn't require specific flags being set on the create file call. So this is where I came up with the concept of combining powers. Like, we've got two types of file-like symbolic links which we can exploit. And we don't require any privilege to do it. And because of the way everything is all sort of hanging together, it's all handling the object manager, the IO manager, we can potentially combine both object manager symbolic links and mount points into one to get file level symbolic links to work. So just do something like this. You have your repass point, which you point to some location in the object manager you can write to. So in this case, RPC control, say. And you put in RPC control an object manager symbolic link with the name of the file you want the symbolic link from. And that can then point to some arbitrary location on the file system. So it does the reparse, it bubbles back up the stack into lookup object manager, and it drops into now parse symbolic link. And parse symbolic link obviously then reads out, say in this case, c:/hello.txt, and it will then go back into the NTFS driver and open that file for you. And what you've effectively done is create a sort of a limited form of a file level symbolic link, which can exist under a directory in the NTFS file system. And that's kind of what you want. Now, one of the problems of symbolic links, which I haven't touched on, object manager symbolic links, is they only last as long as you have a handle to them open. Now, there is a way of getting objects to be permanent, but it requires you to have a particular privilege. And obviously, we're trying to do this without privileges. So if, for example, you have a bug in, say, the profile manager, which I found a few in, you would like to persist this symlink longer than your login session. When all your processes die, all your handles are closed, this symbolic link will go away. But we want to persist it a bit longer. And it turns out that if you call the define DOS device function call, you can actually get it to go to create a symbolic link in any location. It doesn't check that it's a C drive or a D drive. It just goes, hey, I'll create it anywhere you like. I'll follow the symbolic link and create it for you. It's just pretty simple. But crucially, it sets the object permanent flag for you. And if you do it twice, it gets confused and it can't delete it. And it ends up never going away. Or until you reboot the machine. So a few limitations, of course. Obviously, all the limitations of mountain points apply. You need an empty directory, you need to be able to write to the directory, all that sort of stuff. And also, the bundle application can't try and do too much with that mountain point. It can't try and list it, because it's not a file directory, it's an object directory, so it will fail. Things like calling get file attributes may not work, depending on what it's doing. But there's some clever tricks you can mitigate block blocks and all that sort of fun stuff. So at this point, I would demo a zero-day demo. I did this at SciScan, worked beautifully. Unfortunately, Microsoft fixed my bug on Tuesday, so this demo I can't demo. But the advantage of that is I can now talk about it. It's fixed. It's cool. And this is one of these bugs which I think probably if you haven't found it before, you'll kick yourself when you see how obvious it actually is in hindsight. At least I think so. So let's go back to the DOS device prefix. The / question mark. If you try and find this in the object manager, it doesn't exist. Prefix is clearly a lie. It's forced upon you by the object manager in some form. Because what this actually is at least in modern versions of NT, this points actually to a per user, per logon specific path in the object manager, instead of / question mark. So this is so that you can create your mapped drives, for example. If you want to create an X drive, this is where your X drive symlink will go. So, of course, 99% of the time, you're not going to have C colon in there. So how does it find your C drive? Well, that path is actually also shadowed to the global list of DOS devices. So this is where your C drive is, and if it doesn't find it in your per user device location, it will go and look in the actual global. But interestingly, you require no special privileges to write to this DOS device directory. So what happens if, for example, you put in a C colon in there? So I use my tool, I create a C colon symlink, pointed at some arbitrary location, say a different directory. It turns out it honors it. So if you do see the C colon / Windows, it actually lists a completely different directory to what the C drive actually is. Now, that in itself isn't particularly that interesting. You can't easily attack yourself with this because you're not going to gain much privilege by doing so. And you can't use it really as a sandbox breakout because in your limited sandbox, pretty much anything below medium normal level, you're not going to be able to write to this directory. So it actually doesn't sound very helpful until you consider Windows user impersonation. So system services will try and do operations under the guise of the user who's calling. And this is primarily for security reasons. If you're trying to write, say, a file to disk, you don't want to do it at system privileges and have to worry about trying to work out whether that person can actually write to that directory or not. Instead, you get the kernel to impersonate that user, and any then secured operation will run under the context of that user account. The one thing which surprised me when I tested it is that your DOS device directory follows you. And so What you can do, if you can find a system service which impersonates a user, let's say tries to load a library. So it calls load library with a C:/directory. Or you can just point C: anywhere you like. So you can go from C:, it goes into the DOS device name, it goes to your location, because obviously you can write to that, and so you can write your own C: file, which obviously loads some arbitrary DLL on the disk, and therefore you gain privilege escalation. Because that file, even though it's running as you, the process itself is running the system. And so you can obviously just gain system privileges on the input. But of course you might say, load library is not going to get called under impersonation. Well, it probably will actually, but in the general case, you probably won't find many instances of that vulnerability. But what about other functions? Let's take COM as a good example. COM implements a lot of its in-process stuff using DLLs, and obviously, just calling a COM function like co-create instance probably will initialize some sort of DLL and pull it into that process. You can actually extrapolate this out a bit. You can basically say any fucking API call at all could potentially load a library during that operation. Who knows? So as a defensive perspective, it's impossible to secure. So obviously, it had to be fixed. So I found, in this case, the ideal service, in my case, the spooler service, which is obviously dealing with handling printers. So it runs as a local system, which is good. It tends to use user impersonation because it wants to sort of impersonate the user to do certain operations. It's accessible by normal users because that's kind of the point. You want to be able to print. And it does have a habit of loading DLLs arbitrarily from the file system because it has printer drivers, which are generally implemented in some sort of DLL or some other form and will get loaded into that process. So great, you can exploit that, and eventually I'll probably stick out the proof of concept, which will come out when I open the bug up, uses this to gain local system privileges. So that's kind of a cool bug, and that's kind of where the talk would end. But of course, what would be a talk about one more 0 day to demonstrate? So let's hope this actually works. Let's just restart this. So I've got on here my little demo, fully patched version of Windows 8.1, and if I double click it, hopefully give it a second, we get a new command prompt. So if we type who am I in there, we have local system privileges, and yeah, that's exploiting symbolic links to gain local system privileges on a fully patched Windows. So that's basically it. So a few links and references. You can download my symbolic link testing tools. They're pretty simply licensing, Apache 2 license. They're all there. I wouldn't say fully documented, that's probably not true, but they're at least out there and you can read the code. And that file test application, you can just download it, it's open source, you can just do some cool stuff as well. So that's the end of my presentation. If anyone has any questions, then you can fire away.
Who has questions? I see one way in the back. Since everyone actually is in the back.
Hey, how did Microsoft fix the DOS devices vulnerability?
That I don't know yet. I've not had the opportunity to look at it. It still works as a normal user, so I can only presume they're changing the lookup operation when impersonating, but I don't know that for a fact yet. Cool. Thanks very much.
Cool.